Hi y'all, this is section 4.6. It's all about differentiability. So make sure you read through those definitions about differentiability at a point, along an interval, or along the entire domain. We're going to be focusing mostly on the differentiability at a point. So we're going to be talking about, is this function differentiable at some specific x value? Okay. So again, to differentiate just means take the derivative. Okay. And if a function is differentiable, it just means that f at a point, it just means that f prime of a will exist. There will be a dot sitting somewhere along your f prime graph at a. Okay, so we're going to be looking at these six different situations. We're going to state whether the function is continuous, differentiable, both continuous and differentiable, or neither continuous or differentiable. Okay, so if we look at this, actually I would love it if you would stop and try that on your own. See if you can make one of those statements. If you're totally confused, go ahead and press play and see if you can get the hang of it, and then press pause. Try those out. So we're looking specifically at the point x equals c. So only at x equals c. So here at x equals c, we see a nice, what looks kind of like a cubic function, and right here we can see that the function is clearly continuous, and the function is also differentiable because I could draw in a unique tangent line and we could talk about how fast that function is changing at that exact moment. So we would say this is both continuous and differentiable. Okay. Now letter B, clearly continuous, the function's going, and right here it continues to, it doesn't have a break, there is no hole or asymptote there. So we do have a nice continuous function. But if we talked about the rate of change right at that point, because there is a cusp, we could not draw in a unique tangent line. That would be a tangent line, that would be a tangent line, this would be a tangent line. I could sit here forever and draw in lines that would touch at just that one point right there. There would not be one unique tangent line. So because of that, we know that cusps are continuous, but they are not differentiable. Okay? So this cusp is continuous, but we cannot take the derivative at c. Okay? If we looked at what the derivative would look like, kind of looks parabolic here to the left. Function's decreasing. Right about here, changes to increasing, so we know we'd have a 0 for our derivative graph. Decreasing, I know my derivative would be negative. Function's increasing, I know my derivative is positive. Okay, so my f prime graph would look something along these lines. Here at c, we know the derivative would not be defined. And then out of that c value, the function's decreasing at a constant rate. So I don't know exactly what that rate is, but I know it's decreasing at some constant rate, so the derivative would be horizontal. Okay, at some negative rate of change. Okay, so if I looked here at f prime of c, I clearly see there is no value sitting here. I know that the function was not differentiable at x equals c. Okay. You do not need to sketch the derivative functions, by the way. Just wanted to make sure you connect the idea that f prime of c does not exist. That's why f of x was not differentiable at x equals c. All right, letter c. Hopefully we can see here that the function was not continuous. Okay. So if the function is not continuous, there is no way we can take the derivative at that point. Okay? The limit as we approach from the left in terms of the rate of change would be increasing. As we approach from the right, it was decreasing out of that point. But this function is neither continuous nor differentiable. Okay? As soon as the function is not continuous, for sure not going to be differentiable. There's no way, if you don't have a dot, if you don't have a value, continuous from the left and the right, there's no way you can get a value on its derivative. I don't think I'm making much sense here for my words. Hopefully you guys are just watching and not listening. Alright, part D, continuous? No, not continuous, right? You have that hole. So if that hole had somehow, or if that dot had filled that hole, then it would have become continuous, but not continuous. Therefore, neither differentiable or continuous. Okay. Letter E, we have an asymptote here at C. Clearly not continuous, and therefore neither continuous or differentiable. Okay, as soon as it's not continuous, there's no way it can be differentiable. Letter F here, wanted to trick you a little bit. Forrester will do this to you. Probably not the AP test. Notice here is C. We're not asking you about the break over here at C. Okay, so if I asked you about this whole entire function, if the whole entire function was differentiable, we would say no. Okay, but if they ask you if the function is differentiable at C, yeah, nothing special is happening there. We have a nice smooth curve. We drew in a unique tangent line. If that was a perfect tangent line there, there would just be one unique tangent line. So we would say that this function is both continuous and differentiable. Okay. So if you look at all 6 of these situations, you should notice that we got an answer of continuous, okay? We got an answer of both, and we got an answer of neither, okay? Out of the three answer choices, notice that we had continuous, both, and neither. We never got this answer, okay? Because realize that answer is not possible. You could never have a differentiable function that wasn't also continuous, okay? And that's where what we're working towards is really this really important information here, okay? So if a function is blank, then that function is automatically blank. See if you can fill those in with these keywords. Differentiable, differentiable, hopefully I spelled that right, and continuous. And you want to think about which one will go where. If a function is continuous, then that function is automatically differentiable. Okay, does that make sense? Or is it the other way around? Oh, wrong things are moving. Or if the function is differentiable, then that meant that the function was automatically continuous. Okay? Hopefully you're yelling at me, that's the right one, because that is the right one. Okay? If the function is differentiable, then automatically the function had to have been continuous. Does not work vice versa. Okay? So that's what the vice versa one is that just because a function is continuous does not mean that it is differentiable. So just because a function is continuous does not mean that it's differentiable. Okay? And from, I don't know if you have any space at all on your paper, but think about what would be an example of a continuous function that's not differentiable. We're talking about at a point here. And hopefully you can think about a cusp, right? A cusp is continuous, but not differentiable. So that's a perfect example. So we'll have this little statement, and this will probably show up on quickies, and will show up places, in terms of which one implies which one. Okay? So does continuity imply differentiability, or does differentiability imply continuity? Okay, so does continuity imply differentiability? Hopefully I spelled that right. So does continuity imply differentiability, or does differentiability imply continuity? Okay. That is the correct answer, okay? Differentiability implies continuity. So if a function was differentiable, automatically it was continuous, okay? Remember, if you reverse that, it's not true. Just because a function is continuous does not mean it's differentiable, and your cusp is the classic example of that, okay? So what does all of this mean? So we can work backwards, and I would like you to try these on your own, if you would pause and try these. We want to sketch a graph that has these indicated features. Okay, so we want a function that is differentiable and continuous at the point negative 2, 4. So at negative 2, 4, and make sure you label that clearly, at negative 2, 4, we need a nice continuous and differentiable function. So basically it needs to be continuous and it cannot be a cusp, because if it was a cusp it wouldn't be differentiable. So literally it does not matter what happens as long as you go through negative 2, 4 and you have a nice function. Okay, I don't know what I drew there. It looks like Darth Vader's helmet. But you could draw a line, you could draw a parabola, you could draw any type of function that went through that point and was nice and smooth there. Could not be a cusp. Okay. Example number 3 has a finite limit. Okay, so finite versus infinite. So an infinite limit, you know, is like where you have an asymptote, functions continuing to increase forever. This is just saying that there's one specific value we're getting closer and closer to, okay, as x approaches 1. So there is a limit as x approaches 1, there's a value for f of 1, but it's still not continuous at that point. Okay, so let's take this slow. Here at x equals 1, there is a limit. So I like a nice classic linear example of right now, as soon as we have, you know, my limit as I approach from the left equals the limit as I approach from the right, my values are getting closer and closer to the same output. Right now I know that there is some limit. Okay, whatever that value would be my limit. So that's for the first condition. The second condition says there has a value for f of 1. That means if I plug in 1, I get a dot somewhere. So we can call that guy f of 1. Okay. It said, but it's still not continuous at that point. So my picture is perfect because, not perfect like that, but my picture is correct because that dot did not fill that hole. Okay. I'm sure I can't shift it, no. If I could shift it and fill that hole, then it would have become continuous because the output would have equaled the limit. But it doesn't in this case. So we would say that this function is neither continuous nor differentiable at x equals 1. Okay. Alright, now the meat and the potatoes here, if we actually have a piecewise function, and we want to know, is this function differentiable at this point? Okay, so we have f of x equals x squared. So let's just think about what this is. We have x squared, and we know that that would be a nice up parabola. And we're only going to be looking at that to the left of 2. Okay, so if I plug in 2, I know I'm there at 4. So there's my visual of the top branch. And it was just less than 2, it was not including 2. So I know that I would have a hole there at 2, 4. Okay. The other branch is negative x minus 3 quantity squared plus 5. Okay, and that'll be good for all values to the right of 2. So hopefully we remember our shifts. A minus 3 on the inside. I know it looks like we're moving to the left 3, but it's actually moving to the right 3. So that'll mean my vertex is moving to the right 3. The plus 5 will mean it's moving up 5. And then that negative out in front means it's going to be going down instead of going up. Okay, so rough sketch here would mean 1, 2, 3, 1, 2, 3, 4, 5. Boom, there's my vertex. And I'm going down, roughly, somewhere in there. And I'm only picking that up to the right of 2. So only here to the right of 2. And I would be, I'd have a dot there, right? So, don't think I did that very perfectly, but hopefully you get the idea that these are 2 parabolas, and we want to know, are these 2 parabolas, do they meet? Okay, so are they continuous? But more importantly, the main question is here, are they differentiable? Well, realize if functions to be differentiable, it had to have been continuous, and then it also has to be differentiable, which means their derivatives have to equal each other. Okay, so I went straight to the picture to give you a visual, because I want to make sure you're clear that, I moved the wrong thing. If we were to move this curve, we want to see if that does meet up perfectly. Okay, if it meets up perfectly, then we would have a nice continuous function. But we want to know if that is a nice smooth exchange. The way I drew that, it looks like a pretty nice exchange there, that it might actually be differentiable at the point. Okay, but you can imagine if I drew this slightly, I don't know, more steep or less steep, maybe when I came to that point it would be too curvy, and the rate of change coming in from the left wouldn't equal the rate of change coming in from the right. Okay, so we're going to see if it is indeed differentiable at that point or not. Okay, so let me see if I can get this guy to go back to my original sketch. Okay. So sketching will not be your method of deciding whether this is differentiable or not. Okay, because our pictures aren't going to necessarily be exact enough to be able to tell. Okay, so is the function differentiable? Well, in order for the function to be differentiable, it had to have been continuous. So we're going to write our continuous equation. Okay, and then also had to be differentiable. So the rules will be, this continuous equation we already did back in chapter 2 or chapter 3, whenever we would set the 2 branches equal at the rule change. So in order for these to meet up perfectly, I know that this guy has to equal that guy at x equals 2. So I know that x squared would have had to have equaled negative x minus 3 quantity squared plus 5 at x equals 2. Because that's where the rule changed. So if we plug in 2 there, 2 squared equals negative 2 minus 3 quantity squared plus 5. We see that 4 does indeed equal negative 1 squared plus 5. Negative 1 squared would be 1. Negative 1 plus 5 would indeed equal 4. So I have 4 equals 4. So that meant that those 2 branches did indeed meet up at that point 2, 4. Okay. So I know my sketch does look something along these lines. Open circle there, and then the parabola coming out of it did indeed fill the hole. Okay. So I know that the function was continuous, because the limit from the left equaled the limit from the right. Differentiability, okay, the derivatives of the 2 branches will have to equal each other at the rule change. So I'm going to take the derivative of the top guy. So the derivative of x squared is 2x. Needs to equal the derivative of the bottom branch. So that's going to be power rule. We'll pop the 2 out in front. So negative 2 times x minus 3 to the first. And chain rule, the derivative of the inside would just be times 1. So I don't have to worry about that. And then the derivative of plus a constant will just be plus 0. So I'm going to set the derivatives equal to each other at x equals 2. And see if those are equal to each other. So plug in 2 everywhere I saw x. So I get 4 equals negative 2 times negative 1. So I get 4 equal to 2. So does 4 equal to 2? No. Okay. 4 does not equal 2. What this just told me is that the rate of change coming in from the left, okay, which was this branch over here, equaled 4. So if I was to look at the graph of this exactly, as I approached this point from the left, this had a steepness of 4. Whereas I approached from the 2 from the right, that had a steepness of 2. Okay? So if I look back at my picture, it must have looked something along these lines, that I came into that point pretty steep, and then I was only coming out half as steep, so it was only something along these lines. Clearly not a perfect sketch, okay? But the point being that this is not differentiable at that point. It was not a nice, smooth connection, okay? So the rate of change coming in from the left did not equal the rate of change coming out from the right. So therefore, this function was not differentiable, okay? So if they said, you know, yes or no, and then maybe justify your answer, okay, you could say something about the limit of our function, which we had named f of x. We'd be looking at the derivative. So the limit of the derivative, as I approach 2 from the left, did not equal the limit of the derivative as I approach 2 from the right. Okay, we know that the limit from the left was 4, and the limit from the right was 2. Not equivalent. Okay. All right, now I'm probably getting long. Last example. So we want to be able to figure out the values of a and b that are both constants that will make the function differentiable at the rule change. And then we're going to sketch the results and without using a calculator. Okay. So again, if you are trying to come up with the values that make the function differentiable, the function had to have been continuous if it was going to be differentiable. Okay. Remember, differentiability implies continuity. So if the function was to be differentiable, it automatically had to have been continuous. So you have to take those proper steps. Okay. So the continuity equation will be to set these two equal to each other at the rule change. Okay. The differentiability equation will be to set the derivatives equal at the rule change. So the derivative of ax squared, 2 times ax to the first, okay, would equal the derivative of bx minus 2, and the derivative of number times x is just that number at the rule change. So at x equals 3. So you're going to plug in a 3 everywhere you see x. And I'm kind of solving them simultaneously up here. You can solve them one at a time, whatever you want to do. Plugging in a 3. I see 3 squared, which is 9, times a equals 3b minus 2. And this is why we couldn't just ask you if this function was continuous or not. We don't have enough information to solve for a and b just on the continuity piece. We do need the differentiability piece in order to solve. So if I plug in my 3 here, I have 2a times 3 equals b. So I have 6a equals b. And basically now I have one equation with an a and a b, and another equation with an a and a b. And I can substitute in. So you could solve one of these for, or solve this for a if you'd like. I'm going to go ahead and keep this statement, that b equals 6a. And I'm going to replace that fact right here for b. So I'm going to get that 9 times a would equal 3 times whatever b is, minus 2. And b happened to be 6a. So now I have one equation with just a's in it. So I have 9a would equal 18a minus 2. Subtract 18a from both sides. Getting into the summary, sorry y'all. I have negative 9a equals negative 2. Divide both sides by negative 9, and I get a equals 2 ninths. If a equals 2 ninths, if we plug that in right here, 6 times 2 ninths, I do have equal b. That gives us, what, 6, 3 goes in there 2 times, 3 goes in there 3 times, so we're left with b equals 4/3. Okay. So if we put that back into the equation, we would have that f of x equaled, a was 2 ninths x squared, if x was less than or equal to 3. And this is telling us that our b value is 4/3 x minus 2, if x was greater than 3. And so if we had to sketch this, just make sure it's reasonable. Okay, obviously we need to be focused over here at 3 because that's our rule change. So 2 ninths x squared is just a nice basic up parabola. The 2 ninths is just going to make it wider than normal. and still has a vertex of 0, 0. Okay, and if I want to know exactly where I would end at 3, if I plugged in 3, 3 squared would be 9, and the 9s would cancel, so I know I must land here at 3, 2, and I'd have a nice dot there for the top branch. The bottom branch is 4/3 x minus 2. That would mean I'd be going through here at negative 2. I'd be going up 4, 1, 2, 3, 4, to the right 2, to the right 3, 1, 2, 3, boom, right, up 4, 1, 2, 3, 4, to the right 3, 1, 2, 3, and so that line would pick up right there. Okay. And remember, that's kind of the whole point of all this, is to make sure that the graph has a nice smooth transition. Okay. So I always like to think about Jakey's little railroad. You know, he builds his little railroad pieces, and the pieces have to connect nice and smooth so that the railroad, the train can actually run on the railroad. Imagine that you have this railroad, it's really steep in here, but then it's going to connect back up to that rail track. You need to make sure that track is nice and differentiable so that the train doesn't jump its track when it takes that curve. So we want to make sure that the rate of change coming in is the same as the rate of change coming out. Okay, and to assure that, we have to set the derivatives equal to each other, as well as the original functions. Okay? Hope this made sense, y'all. Good luck. Look forward to discussing it with you in class tomorrow.